Okay. Let's suppose that, let me get some markers here. Let's suppose that, before we suppose that, you all know what this means, I think. But if you didn't, and you saw it for the first time, it would be only legitimate that I would say, well, what on earth is that? Well, it's read 5 squared, or 5 raised to the power of 2. But I like the phrase 5 squared. And this actually goes back almost 4,000 years, maybe 1700 BC, to the ancient Babylonians. And to them, numbers represented physical objects, something you could draw or measure. So let's say you had a length of 5, and then you continued to create a square, which was 5 by 5. A question that I could ask you is, what is the area of the square? 25, which is 5 squared, which is why this is called 5 squared, because what we did is we took the number 5 and we made it into a square. Took the number 5, made it into a square, 5 squared. Conversely, we're not dealing with square roots yet, but just for the heck, not just for the heck of it, because I think you should know. If I asked you what is the square root of 49, I'm sure you would say 7. But my real question is not what is the square root of 49. My real question is, why is it 7? And I'm sure your answer is because 7 times 7 is 49. Because 7 squared is 49. The ancient Babylonians, what this meant, and they didn't write it this way, but what they were asking is, what number gives birth to a square whose area is 49? And if something gave birth to you, that's your roots. And I couldn't make this up. That's why this is called a square root. Okay. Oh, but what about this? What about 2 cubed? Well, to the ancient Babylonians, that meant make a cube, which is 2 by 2 by 2. And the question is then, what is the volume of that cube? And the volume is 2 times 2 times 2, which is what this means, and which is what this represents, and which is why this is read 2 cubed. So 2 cubed means just multiply 2 by itself 3 times, and you get 8. And so on and so forth. Now, the geometry, at least for us humans, visually breaks down, but it still actually makes sense. But 2 to the 4th, 2 to the 5th, 2 to the 6th. You know, what on earth does 2 to the 10th mean? Well, it means 2 times the dot times 2, 10 times. Which I think is 1,024. You can do it 2, 4, 8, 16, 32, 64, 128, 256, 512, 1,024, which is hopefully what I said a second ago. Okay, so fair enough. But what does this mean? Now, you may already know, and if you know, it's because you've seen it before. If you have never seen this before, you cannot know, you could not know what this means. Just like if you had never played the game of blackjack, never heard of it, never seen it, never played it, you couldn't know what a face card was worth. Or if you'd never played basketball, you couldn't know what a basket was worth, or football, what a field goal is worth. You can only know these things if you've played the game before, or if someone has told you the rule for this. Now, let me write down something which is going to seem almost preposterously simple. But just hang in there and do it along with me. Let's say we had 2 raised to the power of 3 times 2 squared. Oh, the 2 to the negative business? We're getting there. Now, what does this mean? For example, what on earth does this mean? This means 2 times 2 times 2. And what does this mean? Times 2 times 2. Now, here's what I want you to do. Ready? Count the 2's. You get 5. So this is 2 to the 5th. What if we had star to the 4th, say, times star cubed? You know, what what on earth does this equal, or what on earth does this mean? Well, what does this mean? This means star times star times star. What a symbol I chose here, huh? 4 of them, and then 3 of them. And again, what I want you to do is to count how many stars you see, and there's 7. And we could continue on this way, and I think after a while, what you would think is you would notice that it seems as though if you add these 2 numbers, you get that. And if you add these 2 numbers, you get that. And it seems to be a pattern. And as a matter of fact, it is, which gives us our first, usually people refer to these as rules of exponents. They're not actually rules. In a sense, I've almost given a proof. In a sense, they're theorems, but I'll stick with the regular nomenclature. So if you have something raised to a power times the same thing raised to a different power, you add the powers. These rules are not in any particular order. I think that rule is usually stated first, but they don't really come in any particular order. But so be it. Hey, one thing to notice, really think about this for a second. You saw what I did a minute ago. Look, I did something like, it doesn't matter, 7 squared times 7 to the 5th. You know, what does this mean? 7 times 7, and this right here, 7 times 7 times 7 times 7 times 7. 1, 2, 3, 4, 5, 6, 7. Maybe I've got too many 7s there, but child's play. Super, super easy. Unbelievably straightforward. No question about it. See what's going on. Suppose you had never done any of this before. Never seen any of this, never done any of this. And I just walked in and said, behold, rule of exponents number 1. That actually looks like something very complex or complicated or deep is going on, but not really at all. Now I could do, well here, let's go and do a similar one. I'll just start off with a letter, but I could use a number. So ready, pick a letter, any letter. Okay, T, fine. I don't care what letter you get. T to the 5th divided by T squared. What does all this mean? T times T times T times T times T. 1, 2, 3, 4, 5. And this means T times T. We can do some canceling, and we get T cubed. And, you know, we should do some more examples, but they're in the book. But pretty soon, if not already, you would notice, hey, let's see, 5 minus 2 is 3. And this seems to provide some symmetry with this first rule. And we get our second rule. Again, these are not really in any particular order, but here's our second rule. If we have something to a power divided by the same thing to a power, we subtract the exponents. So just another quick example. Suppose we had 7 to the power of 21 divided by 7 to the power of 18. This would be equal to this, which is equal to this. Much easier to calculate. That's not really the reason why we're going to do this, but fine. Okay. So same base, you multiply, you add the exponents, same base, you divide, you subtract the exponents. Okay, let's just continue on. Consider this. Let's suppose we had u times v raised to the power of 3. What does it mean? You know, deep in your heart and soul, what does it mean to raise something to the power of 3? Well, it means multiply it by itself 3 times. And you can multiply in any order. We have commutative. Multiplication is commutative. So u times u is u cubed, and v times v is v cubed. So we have this thing which I can't help think a little bit like, you know, it's not the distributive rule, but it has a pattern which is not entirely dissimilar to the distributive rule. So here's our third rule, and our third rule says if you have 2 things multiplied and you raise them to a power, you can raise each one individually to a power. Comment I've made many times already in these videos, and I need to make again here. The letter choices here, you don't like these letters, use different letters. Look at 5 different books, you'll see 5 different letter choices. So there is no one particular letter choice which is universally accepted. And the final, oh, I should have told you up front, hey, guess what? There are 4, I don't know, rules of exponents. Again, that always bothers me a little bit because these are not really rules. We're not declaring this. We can prove these based on the fundamental axioms of arithmetic, but that's how everybody refers to them, and I do too. So let's suppose we had this. Let's suppose we had x raised to the power of 3, and then we squared it. Now, what on earth does this mean? Like, what does it mean to cube something? And what does it mean to square something? It means multiply by itself. 1, 2, 3, 4, 5, 6. X to the power of 6. And we can do a few more examples. What you'd see is if you have something to a power and then raise it to another power, you multiply the powers. So here's our fourth rule of exponents. Let's say we had a raised to the power of b raised to the power of c. This is a to the power of b times c. So here are these 4 rules. Should you memorize them? Honestly, yeah, you should. You just do that by practicing a bunch of problems. And this is from 5.2. So if you look in 5.2, you'll see plenty of problems like this. Yeah, I mean, honestly, you really should know these and you really should memorize these. Now, a lot of what you're doing right now, I don't know if anyone's ever told you, but you're really gearing up to take calculus. That's kind of the whole point. I use the wax on, wax off analogy. You're getting ready and getting ready and getting ready and getting ready for what? For calculus. Now, I don't know what percentage of people on planet Earth have ever taken calculus. I know it's less than 50%, and it's probably less than 5%, but I don't have the numbers on it in front of me. Hey, we could Google that. So most people never get there. They learn these things and they don't fully see why on earth anybody would want to know these things. But I'm assuring you, yes, there are good reasons to know this. Now, there are 2 strange consequences of these rules. What I was thinking of a second ago is, hey, why shouldn't I do this like I normally do? I suppose I should. This is the moment where I usually talk about spelling. Sounds like an odd thing to do. Why would I be talking about spelling? Well, it ties directly into what I'm about to show you. Spelling is also something that's driven me crazy my whole entire life. I've always had a hard time spelling words. I read a lot. I'll challenge anybody to a vocabulary quiz. But spelling has, and I've taught English grammar, blah, 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 blah. But spelling, ooh, that has tormented me my whole life. Words that most people find very simple to spell, I have a heck of a hard time spelling. Well, when I was a little kid, they told me to sound it out, and now I know you can. English is not a phonetic language. In fact, we have homonyms. So there, weather. So that's a demonstration. That's a counterexample to the idea of sounding something out. You can't. And, but I didn't know how to say that as a little kid. So fine. But even if I failed at sounding it out, then they would tell me to use spelling rules. And everybody's favorite is the old classic I before E except after C, or when it sounded like A as in neighbor and wait. I didn't know this as a little kid, but I wish I did. I wish I could go back. And I would say, how about weird, which is W-E-I-R-D? Well, that violates that rule. How about protein? That violates that rule. And I bet somebody out there has a list. There's at least a dozen or more words that violate that rule, which means it's not much of a rule. At best, it's a rule of thumb. At best, it's a guideline, but it's not a rule. Here's the deal. In football, a field goal is worth 3. Doesn't matter whether it's Monday night. Doesn't matter whether it's Sunday morning. Field goal is worth 3. In the game of blackjack, a face card is worth 10. Doesn't matter whether you're in Monte Carlo or Vegas or out in the East County or in San Diego. In sports, in other games, card games, board games, the rules are fixed and we want them to always work. We don't want exceptions to the rules. And the same thing applies to mathematics. We want our rules to always work. And that includes these rules right here. Now, keep that in mind. See these 4 rules? We're going to insist that these rules work. Always. Again, before we start playing the game of mathematics, or from here on out, we're saying moving forward, see these 4 rules? They shall always work. No matter what, they shall always work. So, ready? Somebody pick a number. 8. Okay, fine. I didn't care what number you chose. Could have chose 2. Could have chose 79,317. I don't care. Fine. 8. Consider the following. 8 squared divided by 8 to the 5th. Now, what does this mean? 8 times 8. What does this mean? 8 times 8 times 8 times 8 times 8. See, 1, 2, 3, 4, 5. Let's just do some good old-fashioned fraction work. That goes in there once, that goes in there once, that goes in there once, that goes in there once. So what do we have on top? 1, and what do we have on the bottom? 8 cubed. Now, there is no question about that. That's just using basic, ordinary arithmetic. Let's apply this rule right here. How come I can apply that rule? Because we just declared that we are going to insist that these rules work all the time. If I use this second rule and I apply it here, let's see, make sure everything's on screen here. What would I get from this? Here, let me write it down here. What would I get? I would get 8 to the power of 2 minus 5, which is 8 to the negative 3. And what that means is the following. We're going to have to insist, we're going to have to declare or define that 8 to the negative 3 shall mean 1 over 8 cubed. Now we're declaring that. Think about this for a minute. What I'm saying is you can't, quote unquote, figure this out. It's not figure outable. How come this is equal to that? Because we declare it. So here's what we're declaring. Let me erase this. As a consequence of these 4 rules, we're going to have 2 declarations, 2 definitions. One is this. Anything raised to a negative power shall be 1 over that thing to a power. Now we're declaring this. We're not proving this. We're not figuring this out. We are declaring this. So, for example, what is 2 to the power of negative 5? It's 1 over 2 to the power of 5. How come? Because. That is the answer. Because. And the reason I'm emphasizing that is I've seen many people over the years struggle and rack their minds, and they're trying to figure out why is this equal to this. Why? It's equal to that because. It'd be like trying to go, why is the jack of clubs equal to 10 in blackjack? And they're staring at the card and they're trying to, you go, no, you don't get it. It's worth 10 because we say so. And this is equal to this because we say so. And then 2 to the 5th, well, 2 times 2 is 4, 8, 16, 32. So 1 over 32. So that's our first, I was almost going to say strange declaration. It's not actually strange, especially once you get used to it. Now, sticking with the same number, although it doesn't really matter, picking a different number, 73 divided by 73. There's no question that's equal to 1, or at least I don't think there's any doubt about it. On the other hand, look, this is equal to this. Somewhere along the way, we probably should have said anything to the power of 1 is just equal to itself. Let's apply the second rule to this. Apply the second rule right here. 73 to the 1 minus 1. What's 1 minus 1? 0. What does this tell us we have to do? We have no choice. Anything raised to the power 0 shall be 1. We have to make it so. We're declaring this. So don't try to figure out why this is the case, but anything raised to the power 0 is 1. We're declaring that. We're defining this. So don't drive yourself crazy trying to figure out why that is the case. Hey, there was one exception. In what I just did, and the thing I just did, I wouldn't have done this. 0 divided by 0, because this actually doesn't have any meaning. I should probably show you why it doesn't have any meaning, but it doesn't have any meaning. So when I took 73 divided by 73, I could have taken any number and divided it by itself except 0. So what you'll see in our book and any textbook is off to the side right here. Off to the side, you'll see a little comment and it'll say x is not equal to 0. That's not going to come up again in this course, but that is something that needs to be mentioned. Yeah, so hey, what's the square root of 517 divided by 92, all raised to the power of 0. 1. How come? Because anything raised to the power of 0 is 1. Let me just finish this video by saying something that you might not have seen before. And you could live the rest of your life and never know this. And that's okay. You'll have a happy, fruitful, fulfilling life, hopefully. You've all heard you can't divide by 0, but why? First off, what on earth does division mean? Consider the following. What's 12 divided by 3? 12 divided by 3 is 4. That's not my question to you. My question to you is why? Why? How did you know that? Probably because you knew that 4 times 3. So I'll say because 4 times 3 is equal to 12. Or let's say, what's 20 divided by 10? 2. And why is that? Because 10 times 2 is equal to 20. So what is the definition? What is the definition of division? If someone had never done division before, now there's various ways you could answer it. One is it's actually kind of a shortcut for subtraction, but you would say how many times does 3 go into 12? But if you had to write it down succinctly, quickly, what you would say is A divided by B equals C. Every once in a while, there's some real official or formal terminology that mathematicians use, and we don't really need to get into it here, but because I'm videotaping this, part of me is always thinking, there's a part of my brain that's always thinking, what would anybody thinking if they're watching this? I want to write down if and only if or IFF or this is equivalent to, but I'm just going to say in a little bit simpler way, what does this mean? What does this mean? Hey, look, a new word. You learn a new word. You don't know what the word means. So what's one thing you try to do? Is find a synonym for that word. Now, it doesn't always happen, but if one's available, fine. So what does this mean? This means B times C is equal to A. And what I've done is I've explained this concept division in terms of multiplication, which is an easier concept. The same thing you do, and what is, 7 times 8 is 56, but what is multiplication? It really says you take 7 eighths, add them up, or you take 8 sevens and add them up. So multiplication, you explain you explain it or define it in terms of addition, a simpler operation. So division, we're defining in terms of multiplication. Okay, now pick a number, any number. 9, fantastic. What's 9 divided by 0? Let's say it's a mystery. I actually heard a teacher years ago, a new teacher. I'm not going to give away any names, and it wasn't at Mason, it was somewhere else. And they said, well, this is really complicated, we can't get into this class. No, wait. So let's say there's a mystery answer to this. And no, it's been kept secret, and no one ever told you, but there really was an answer. So let's say it's the mystery. Let's just say M for the mystery number that's been kept secret. If this was true, then 0 times M would have to equal 9, according to the definition. 0 times what number equals 9? And the answer is no number. There's no solution to this equation. And that's why you can't divide by 0. Oh, wait a second. What about 0 divided by 0? No. What about 0 divided by 0? Anyone know what the answer is? 91. I don't know how you knew. Fantastic. How come it's 91? Because let's use the definition, because 0 times 91 is equal to 0. But wait a minute. I could have chosen any number. I didn't have to choose 91. I could have chosen the square root of 2 or pi or 3 or Avogadro's number, which we'll talk about one of these days. So the deal with 0 divided by 0 is it really could be anything you want it to be, and that seems a very unsatisfactory situation. So what we do in mathematics is we prove you can't divide a non-zero number by 0 because you can't by definition, and we are not going to divide 0 by 0 because it leads to a very unsatisfactory situation. So you've heard your whole life you can't divide by 0, and that is true. You heard right. You can't divide by 0. So what do we have now? We have the 4 rules of exponents. We know what it means to raise something to a negative power, and we know what it means to raise something to the power of 0. You get 1. All right, so that's enough for this video. Next video coming soon.